jump back into some calculus. At this point, we have discussed the chain rule and we introduced implicit differentiation. And we're going to just dig more, dive a bit further with implicit differentiation and actually applying the rules or techniques to application problems, such as related rates. So I am going to share my screen and we're going to jump right into some more problems. Like I said, we did look at some problems with implicit differentiation. We're just going to pick back up with where we stopped previously. So let me share my screen. Okay, so this first problem is very similar to one that we looked at previously. It is introducing us now to a third variable, and that is actually what we're going to take the derivative uh, towards or for. So we're told here that x and y are functions of t. And when we look at the related rates problem, t will of course represent some time. But we're going to evaluate dy dt, which is the derivative of y with respect to t, for this equation, okay? And also with these given conditions. So we're going to be given the derivative of x with related to t, with respect to t, and then we're given the actual value of x and the value of y. So I'm going to start off by rewriting the equation, 4xy minus 7x plus 6y cubed equals negative 138. So what I want you to notice first is this very first term is a product. It's a product of x and y. So I need you to remember that we have a specific rule when we're dealing with a product that we want to differentiate. So I am starting off first with just expressing this as what we're about to do as the derivative with respect to t of 4xy minus 7x plus 6y cubed equals a negative 138. So I'm just showing that I'm going to take the derivative with respect, and this is number 11, from section 2.3 in calculus in 1830. All right, so I am taking the derivative with respect to t, okay, keeping in mind that I have variables x and y, all right, but they are functions of t, okay? So looking at this first term, it's a product, so we're going to apply the product rule. So we're going to say first, and I'm going to keep the 4 with the x. I'm just going to say that is with the x here. So I'm going to say first times the derivative of the second plus the second times the derivative of the first. Okay, so I've got first, and this is just the product rule. Okay, so I've got first times the derivative of the second, which would be the derivative of y would be technically it would be y prime, but remember we're expressing this in terms of t. So instead of writing y prime, we're going to say the derivative of y with respect to t is dy over dt. Okay, prior to this example, we had just been calling the derivative of y prime. Okay, but we're calling it now because we're talking about with respect to t, we're calling it dy over dt. Okay, so that's first times the derivative of the second, and then we're going to say plus the second, which is just the second, which is just this y, times the derivative of the first. The derivative of 4x is just 4, and I will put that in front, but right now it's just 4. And then we say, of course, dx over dt. Just like we took the derivative of the y, we take the derivative of the x with respect to t. So the difference is, though, when we took the derivative of the 4x, we took the outer derivative, you can kind of call that. That's where if you have a linear term, the derivative of a linear term, which in this case 4x, is just the coefficient, just the constant 4, and then we take the derivative of the inside with respect to t. So that's where we get the dx over dt, okay, for that. So we apply the product rule. Then the next term, we've got a negative 7x. So I'm going to go ahead and put the minus there because that won't change. The derivative of 7x is 7, and then times the derivative of the inside, which is dx over dt. So it's as if you apply the power rule to the outer part, or you take the derivative of this linear, and that's how you just end up with a constant. And then you take the derivative of the inside, because keeping in mind, this is a function of t. X is a function of t. So the derivative of x with respect to t would be dx over dt. Okay? Then we're going to do something similar here to this one. We're going to take the outer derivative where we apply the power rule. We'll bring down that old exponent. So I still have that plus there, but that's going to now be 3 times 6 because that 3 is going to come down. And if you need to see that, and we'll just rewrite it, we'll go ahead and do that. So we're taking the outer derivative, and that new exponent is now squared. And then we take the inside derivative, because remember, y is a function of t. So that would be times dy over dt. Okay? And then that's equal to the derivative of a constant. That's just 0. Okay? So I'm going to clean this up a little bit, and then we'll plug in our conditions and figure out what's missing or what we're trying to find, which we already know. We're trying to get dy over dt. So let's clean this up a little bit. So right now we got 4x dy over dt plus 4y dx over dt minus 7 dx over dt plus 18 y squared dy over dt equals 0. Okay? Now let's evaluate at the given conditions. Okay? So I've got dx over dt, that's negative 18. I don't know dy over dt, but I do have dx over dt, and I've got x, and I've got y. So this is going to be 4 times 6, because the x is 6, dy over dt, plus 4 times the y, which is negative 2, times the dx over dt, which is negative 18, and then plus 18 times y squared, which is negative 2 squared. Okay, y is negative 2 squared. And then again, dy over dt equals 0. Okay, so this is what we have right now. Let's clean all this up. So 4 times 6, that's 24 dy over dt. Negative 8 times negative 18, that's a positive 144. And then we've got 18 times 4, because that negative 2 squared becomes 4. So 18 times 4, that's 72. And then we got dy over dt still there, equals 0. Okay? So let's continue on here. Uh-oh, did I leave something out? I did. I left off this middle term right here. I jumped from here. That's 4 times y times dx. Right here, I've got negative 7 times dx over dt. So I need to stick that in there. Negative 7 times negative 18. That is plus 126. My apologies, you guys. So that term right there, I didn't translate that down. I didn't bring that down. I jumped from here, these two terms right here, and then I moved to that. So I left that out by mistake. Okay, so that is going to combine with 144. That 126 and 144 will combine. So right now I've got 24 dy over dt plus 270, and then plus 72 dy over dt equals 0. Okay, So continuing to clean this up a bit, we can go ahead and take the 270 to the other side. So we can say minus 270. And then that gives us 24 dy over dt and 72 dy over dt. So 24 and 72 combine to give us 96 dy over dt. And we've got equal to 270. Okay. And then we divide by 96. Dy over dt equals, let's see if that will simplify. Negative 270 divided by 96. It gives us a decimal. And I am not sure if they want the decimal or a reduced fraction. I'm going to take a peek here at the solution and find out they want the fraction. So that simplified becomes negative 45 over 16. Okay. And again, just make sure when you're, especially when you're dealing with several terms like this, that you don't rush and mistakenly leave one out, because we took the derivative and then I just completely overlooked that right here. Okay. Okay. All right. Let's look at number 12. Let's see what we're dealing with here. And I think this is actually our first application, our first real application problem. So it says a boat is being pulled, looking at number 12 here. A boat is being pulled toward a dock as shown in the figure to the right. Okay, so this boat is being pulled closer and closer to that dock. If the rope is being pulled in at the rate of 1 foot per second, so that's the rate this rope is coming in or decreasing. The length of the rope is decreasing because it's being pulled in at 1 foot per second. How fast? Okay, so I'm going to underline fast. That means we're looking for a rate. How fast is the distance between the dock and the boat decreasing when it is 2 feet from the dock? Okay, so let's see what we're dealing with here. I am looking at this right triangle here. You can see that we've got a right triangle formed from the distance between the boat and the dock to this 2 feet here that the dock and the boat, or sorry, when it's 2 feet from the dock, I'm sorry, that 2 feet is there. And then the length of the rope here. So I'm going to call this, of course, since it's the hypotenuse, because I'm dealing with a right triangle, I'm going to call that C. I'm going to call this adjacent side A. And I'm going to call this side B over here. Okay. So let's see what we know. Let me get some paper here. It says the rope is being pulled. So I'm going to jot that down. This is number 12. Now, when you're dealing with these related rates problems, sometimes a formula would jump out at you. I don't know if this jumped right at you when you were looking at it, but you are dealing with a right triangle. When I see a right triangle, I tend to lean towards trig functions or Pythagorean theorem, okay? And in this case, I'm definitely dealing with the Pythagorean theorem because I don't know anything about the angles, but I know some things about the sides of the triangle. So we're told that the rope is being pulled in at a rate of 1 feet per second, okay? That means the length of C, the length of this rope, is decreasing at a rate of 1 feet per second. So the length, because if the rope is coming in, the length of the rope, which is C, but side C, is decreasing at 1 foot per second. Okay, so since I already know that this is side C, then that means my rate that is decreasing is called dc over dt, because that is the rate that C is changing with respect to time. So dc over dt is equal to that -1 foot per second. And it's negative because it's decreasing. Okay? We want to find, this is what we're looking for. It says, how fast is the distance between the dock right here and the boat decreasing when it is 2 feet from the dock? So in other words, we want to find the rate that A is changing when the length of A is 2 feet. Okay? So we want to find how fast A is changing or decreasing. In this case, we're specifically told decreasing. When A is equal to 2. So we're looking for the rate of change of A, dA, with respect to t. That's what we want to find. This is our unknown. This is what we are going to try to find, dA over dt. So since we know what we're looking for, since we know we have this right triangle, and because the right triangle doesn't tell me anything about the angles except for the fact that I have a right angle, I don't know anything about the two acute angles, I'm leaning towards Pythagorean theorem, because not only did they tell me B up front, I was told I see this length of B is 2 off top, but then they also tell me what A is, and we're interested in the rate of A when A is 2. So we know A as well. So we know two sides. So we're going to use Pythagorean theorem. There. So we're going to write A squared plus B squared equals C squared. Okay? All right. Now I know I'm going to take the derivative because I'm looking for a rate. All right. However, I don't want too many unknowns. That's already the unknown that I'm, trying to find. But in addition to that unknown, I don't know C yet. So the first thing I'm going to do is, before I even differentiate this Pythagorean theorem equation, the first thing I'm going to do is use it to find C. Before differentiating, I gotta spell this right. Got it. Before differentiating, find C, okay, using the Pythagorean theorem. So I know we're letting A be 2, so I'm going to go ahead and replace A with 2. We're told that B, this opposite side here, is 2. That was a given. That was a constant, basically. No matter what the rates are doing, that side B is 2. So that's also 2 squared, and then we're going to say equals C squared. Okay? So 4 plus 4 equals C squared. So that's 8 equals C squared. So C is the square root of 8. Okay? So since we know C, now we can go ahead and differentiate, and we'll replace in our new equation that we're going to have with the derivatives, we'll replace these values. We'll replace these variables A with their A and C, and of course dc over dt will replace those into the new equation we'll form when we take the derivative. And of course we're talking about the rates changing with respect to time. As time moves, the rate, this one in particular, is decreasing. So we're taking the derivative of this equation, of this Pythagorean theorem, with respect to time. So derivative of A squared plus B squared equals C squared. But I am going to go ahead and put that constant, B is a constant. So I'm going to go ahead and replace that with just 2 squared equals C squared. We can go ahead and say that's just 4. I actually should have written that before I even put d over dt out here. But it's okay because I haven't actually taken the derivative. Now I'm about to, okay? So this is just a constant now. All right, so I take the derivative of A with respect to t. So that's going to first be the power rule. I'm going to take or apply the power rule to the exterior to the outer equation, or the outer exponent. So that 2 is going to come down. So that becomes 2a. And then the derivative of a with respect to t would be dA over dt. Okay, because we have to think about the inner function, a, being a function of time t. All right, then we move on. The derivative of a constant, that's just 0. We got our equal sign. Then the derivative of c, also, we apply the power rule. We bring down that 2, that old exponent of 2, so that becomes 2c. And then times the derivative of the inner function with respect to time t, so dc over dt. Okay? So we're going to evaluate this. We're going to find this unknown dA over dt, solve for dA over dt, solve for the rate of A. Okay, how fast A is changing, or how fast A is decreasing when A is 2 and when C is square root of 8. Because keep in mind, we solved for C, and they told us to find the rate when we let A be 2. So right here, I've got 2 times 2, because A is 2, dA over dt. I'm going to drop off that 0. So that's equals to 2 square root of 8 times dc over dt. We know that's -1. So we're going to go ahead and put that in as -1. Now, this particular problem, I believe they want us to give the answer as a decimal because it's an application. It's a real world situation. So when we talk about time or rates in an application type problem or atmosphere, we of course would use a decimal, okay? That corresponds to a more real world situation than giving a reduced fraction, okay? So cleaning this on up a bit here, 2 times 2, that's just 4 dA over dt. And then this is equal to, right here, let's put it in. Let's put that on in the calculator. So let's say 2 times the square root of 8, and then it's times -1, but that just makes it negative. But let's go ahead and put that. So that's a -5.656854249. Okay, I'm gonna give that decimal. I kept every decimal point, or every decimal place. I didn't have to, but I tend to like to be more exact at the end, so I wait till the end to round. So I'm gonna now divide by 4, and so dA over dt is gonna equal that divided by 4, which is a -1.414. And I suspect that we're rounding to either 2 or 3 decimals. I wrote 3. Let's take a look here. Yeah, nearest thousandth. On number 12, it says nearest thousandth, so that is 3 decimals. Okay. Hopefully this is making more sense for you. We're going to look at another problem. Okay. All right. Okay. Let's see what we got next. How about number 13? Let's take a look. And I believe on your reference sheet, your fact sheet, I did give you that first page. I believe the first couple of pages relate to algebra and just some formulas that might come in handy, might be useful. That would be applied to number 13. Let's take a look at it. It says the radius of a spherical balloon is increasing at the rate of 0.6 centimeters per minute. So we're talking about how the radius is increasing. So this is the rate of the radius, okay? It says how fast is the volume changing? So that means we want to find the rate of the volume, okay? We want to find the rate of the volume. Well, we know volume is V, so we're looking for the rate of V. That means we're looking for the derivative of V. Okay. How fast it's changing when the radius is 7.1. That's what we're given. All right, so when I think about this particular problem here, volume of a sphere, that is a formula, specific formula that we'll use. And notice that it's cubic units. So that kind of helps reveal a little bit what formula, but we're using, and they tell us right here, volume, and then they tell us here. So we're looking for the volume of basically a globe, a sphere. So this volume formula would be V equals 4/3 pi r cubed. And again, this is on your fact sheet, your reference sheet. This is not a formula that I expect you to just memorize. Now, the thing is, though, even if you have the formulas on that reference sheet, you have to understand or recognize which formula to use. That's the thing. I'll give you the formulas, but you do have to recognize when to use it. Okay. Like number 13, again, we're talking about a sphere and we're talking about volume. Okay. All right. So this is the formula that we're using. All right. And we are given, let's see what we're given. Given the radius is right. So keeping in mind, this is with respect to time. This is 0.6 centimeters per minute. So given the radius, the rate of the radius, that would be dr with respect to time, dr over dt, which is 0.6 centimeters per minute. And we want to find dv with respect to time t when r, the radius, is 7.1 centimeters. Okay. So we have two values that were given that we will somehow use them, apply them to the formula once we differentiate, okay? And that will then help us to find what's unknown. So I'm going to take the derivative with respect to time of this formula, of this equation. V equals 4/3 pi r cubed, okay? Now, I don't want you to get confused here. Pi is a number, okay? So we do not apply the product rule here. 4/3 is a number, and so is pi. So technically, this is a constant or a coefficient, and then you got r cubed, okay? So I just want you to keep that in mind, all right? So when we take the derivative of v, basically the derivative of v with respect to t is just dv over dt. Okay, and that's the only thing on that side of the equation. So we've got that equals. Now here, the r is the variable. Remember, these are numbers. These are constants. These are coefficients. Okay, so the r is the variable. So we're going to apply the power rule by bringing down the 3, and it will then just kind of be out here, going to get multiplied to 4/3 pi. And so that's then r squared, okay, because we reduced the exponent. And then remember the radius, all right, we're going to differentiate r, but remember it is a function of time. So the inner derivative, the derivative of r itself with respect to t, would be dr over dt, okay? So we want to find dv over dt when we have the rate that r is changing, which is increasing, and when r is 7.1. So plugging everything in, let's clean this up a bit though. The 3's cancels. This is 4 pi r squared dr over dt, dv over dt. Okay, so all I did was just that 3 that I brought down from that exponent, just canceled out with that 3 that was on bottom. Okay. All right, now plugging in everything else that we know. Remember, we're looking for dv over dt. We're looking for the derivative of the rate of the volume. So this is 4 pi r squared, so that's 7.1 squared, times dr over dt, which is times 0.6. Okay? So we have 4, we have times pi. I'm going to use the pi symbol on my calculator. I'm using the actual pi symbol. Let me see if I can scoot it up so you can see it. It's right there, the second function of this little housetop here, rooftop. So 4 pi times 7.1 squared, and then times 0.6. So I'm just putting that all in, and we get approximately 380.0824. And we are told to round this one, let's see, to one decimal. That's going to be 380.1. Okay? That is the rate that the volume is changing per minute. Okay? I hope this is making more sense. We have another one, number 14, that I want to look at. And again, we have to consider what formula is going to be needed for it. So that was number 13. Even though we may have not recognized right away what formula to use, once you get in the habit of thinking about Pythagorean theorem, if you've got some solid shapes, think about their volume formulas, because I think we may have another volume formula for number 14 also. Let's take a look. So, yep, right there, I see V, volume. So number 14 says an oil tanker aground on a reef is forming a circular oil slick about 0.2 foot thick. Okay. To estimate the rate of the volume, okay, dV over dt, at which the oil is leaking from the tanker, it was found that the radius of the slick was increasing at 0.31 feet or foot per minute. Okay, so that's the rate of change of the radius. Okay, increasing, that's why it's positive. And it says when the radius was 400 feet. So we want to find dV over dt. Okay, so let's see, what do we know right now? All right, we've got a circular cylinder. If you think about it, it's a oil tanker. So I want you to think about the volume of a cylinder on number 14. So kind of like this shape. Okay, so volume of a cylinder, that is pi r squared times h. Okay, and this is where h is the thickness. Let h be the thickness, because we only have two variables, r and h. Okay, we already know r is the radius, and they give us the rate at which the radius is changing. So this other value that they provide for us, that constant value, 0.2 foot thick, we're going to let that be the thickness. We're going to let h be the thickness. Okay, because we know it can't be r, and we literally have only two variables if you don't include volume, three if you include it. Volume, radius, and the h, the height. We're letting that become thickness. Okay, so I am going to first off go ahead, since h is given, I'm gonna go ahead and put that in as a constant, because no matter what the rates are doing, that stays the same. So I'm gonna go ahead and put that in as v equals pi r squared, and then h is 0.2. Okay, and we can, of course, since that's a decimal number, go ahead and pull that to the front. So 0.2 pi r squared is what we're working with. Okay. All right. So I'm going to differentiate this, because keeping in mind, we want to find dV over dt. We want to find the derivative of the volume, the rate of the volume. That is essentially what dV over dt is, the rate of the volume. Okay. So we're going to differentiate it. So let's take the derivative with respect to t of v equals 0.2 pi r squared. So when we take the derivative of v, okay, the derivative of v with respect to t is dv over dt. Okay, now this is a number. This is just a coefficient. This is just a coefficient as well. Of course, we can multiply them together to get something, even basically some decimal. But I'm just going to let it hang out, and I'll clean it up later on here in a little bit. So I'm going to take the derivative of the r squared. So I got to think about the outer derivative. That's an exponent. So that 2 is going to come down. And so that's now r to the first. And then we have to consider the derivative of the inside function. Well, the inside function r, well, r is a function of t. So the derivative of r is dr over dt. Okay? So continuing to clean this up a bit, 2 times 0.2 is 0.4. And we've got pi r times dr over dt. And we were told that we want to find dv over dt. That's what we are looking for. And we were given the rate at which r was increasing. So we were given dr over dt. They used a capital R, I used a lowercase r. It makes no difference, okay? So, and I'm going to scoot this up some. I hate to cover the picture and everything, but I think we're good. I don't think we have to see it. But I do want to write that down. That is 0.31. And again, it's positive because the rate is increasing. The radius, I'm sorry, the radius is increasing. And this is when, we're trying to find the volume, when this is the rate of R and R is 400, when R is 400. So putting these values in, 0.4 pi times 400 times 0.31. And we will, of course, multiply that all together. So we've got 0.4 pi times 400 times 0.31. Okay. All right. So that gives us approximately 155.8. How many decimals are we going here? This is number 14. We're told to round to the whole number. All right, so that's going to be 156 because it's 155.82. So as a whole number, that's 156. Okay. The more you practice, the better you'll get at these. And I think you might even start liking them a little bit. They're actually, that's one beautiful thing about calculus that sets it apart from other math topics or math courses. It's really applicable to real world. So it can make more sense for you when you can connect it. Okay. Whereas, in algebra, we would say solve for X. And why are you solving for X again? You don't know. It's just what you're told to do. But when you can literally apply it to real world situations, I think it just connects better. Okay. All right. So let's do one more problem. The last one here. Might as well knock 15 on out. And then we'll be done with our discussion on implicit differentiation and related rates. And again, related rates, just basically application problems, okay, of implicit differentiation. So let's take a look at this. It's got a couple parts here. It says, suppose that, and this is a good thing, you actually are given the equations here. It says, suppose that for a company manufacturing calculators, the cost, revenue, and profit equations are given by. So we got cost, we got revenue, and then we're told that profit is revenue minus cost. So even though it's not provided, we can easily determine that equation by actually setting this up, R minus C. And this is where the production output in 1 week is X calculators, okay? So in other words, your revenue, your cost, and your profit functions are functions of you got your variable X, they're written in terms of X, but they are functions of time T. As time moves, your costs may increase or decrease, your revenue may increase or decrease as time progresses. So they're functions of T. So for part A, it says, oh, sorry, let me read that first. It says if production is increasing at a rate of 600 calculators per week. So I'm going to underline that. So that's how we know we're dealing with a rate that's related to time per week, okay? So if production is increasing at a rate of 600 calculators per week, so this is right here, this statement, it says where the production output in 1 week is X calculators. So we're talking about the rate of X. okay? Production of X calculators, this is the rate of X. So that means this is dx over dt, okay? So if the rate is increasing at 600 calculators per week, when the production output is 4,000 calculators. So this is the rate when X is 4,000. So they're giving us another value there. We want to find the rate of increase or decrease in cost, revenue, and profit. So for part A, we want to find the rate of increase or decrease in cost. So we're talking about costs first. Costs are blank at the rate of blah, blah, okay? So on part A, we want to find the rate of change of cost. So that would be DC with respect to T, differentiating costs with respect to time T, okay? So we're going to start there. We're going to take the cost function or the cost equation, 70,000 plus 30x, okay? So we are going to find dc over dt. We're going to differentiate. So we're going to take the derivative with respect to t of this function. So I'm just rewriting it, okay? So when we differentiate, when we take the derivative of c, that is just derivative of c with respect to t, dc over dt. Then equals, this is a constant. The derivative of a constant is 0. Okay, moving on here. 30 is a coefficient. So the derivative of 30x becomes 30 because the derivative of a linear term becomes a constant. And then times the derivative of the inside function, because remember, x itself is a function of t. So the derivative of x with respect to t would be dx over dt. So essentially, we have dc over dt equals 30 dx over dt. Okay? So that would just be 30 times 600. Because remember, we're told that the derivative for x, okay, production, the rate at which production is increasing, the derivative of x is 600. So 30 times 600, I know that's 18,000. Okay, that is the rate at which the cost, that is the rate of the cost, I'm sorry, the rate of change of the cost, I should say. So part A says costs are blank at the rate of 18,000 per week. This is positive, so we say increasing. Okay? So as production increases, costs increase, which should make sense. Okay? Let's see what else we have. Moving on to part B here. So part B says revenue. So we're looking for the rate of change of the revenue function here, okay? So that would be part B. I may have to get another page here. I'm going to try to still show that, but then scooting this up. So we're looking for dr over dt, the rate of change of the revenue function or rate of change of revenue with respect to time t. So we've got r equals 200x minus x squared over 20. Okay, and so we're going to differentiate with respect to time t. R equals 200x minus x squared over 20. Okay, so let's do the differentiation. So the derivative of r, that is just dr over dt, derivative of r with respect to t, equals the derivative of 200x, the derivative of 200x, that is going to be 200 times dx over dt. Okay, the derivative of the linear, just becomes a constant. And then remember, x is a function of t, so the derivative of x itself is dx over dt. Okay? Then we've got negative x squared over 20. Technically, that over 20, 1 over 20, because that's essentially what we could say, 1 over 20. It's just a coefficient. So really you can, if you want to, you can pull it out front and just kind of write it like this, if that helps you. And then differentiate the x squared. So that becomes 2x, because you're bringing down the exponent 2 and lowering the exponent by 1, okay? So you had the 1 over 20, because that's what this is here. Remember, when there's no coefficients, understood to be a 1. So all we did was just write that as 1 over 20. And then we differentiated x squared as 2x, and then times dx over dt. We got to take the derivative of the inside. Remember, it is a function of t. So cleaning this up a bit, just because you don't really have to, you can go ahead and plug everything in. But I'll clean this up a bit first. 2 over 20, that becomes 1 over 10. Okay? And then we got x dx over dt. And now, and that's equal to dr over dt. And now I'm going to plug in my values, the values that I'm given. Okay? So we've got 200. dx over dt, that's 600, minus 1 over 10. The x, remember that was 4,000. We were given these values. Trying to find the rate of change when x is 4,000 and the change in the production, or the rate of change of the production was 600, dx over dt. So that x right there, that's 4,000. And then dx over dt, again, that's 600. Okay, so whipping this on in, 200 times 600, if you want to go ahead and get that answer, what is that, 120,000? And then 1/10 times 4,000 times 600. So that is 240,000. And we are subtracting there. So 120 minus 240, we get a negative 120,000. So this means it is decreasing. The revenue is decreasing. Okay, as production increases. And that is because the costs are increasing. So you have more costs, revenue might tend to go down. All right, that's why a lot of mass production companies, the more you produce, usually you can keep costs lower. But anyway, that's neither here nor there. So part B, we have a decreasing revenue rate at 120,000. So you put decreasing, but you just put the actual value amount there. Don't put negative there, okay? You take care of the negative by writing decreasing there. Okay? All right. There's one more part here, part C. Part C, we want to find the rate at which the profits are either increasing or decreasing. So, of course, we got to get a profit equation. So the first thing I'm going to do is that. Find profit equation, or write profit equation first, or function, equation, function, whatever you want to call it. So P equals R minus C. So that would be P equals 200x minus x squared over 20 minus 70,000 plus 30x. Okay, so we are just basically subtracting these two functions. Sometimes if you have like terms, you'll bring them together. We should have at least one pair of like terms, but let's just take the subtraction, the minus through first, so that we can then combine like terms, because we can't do that until it's out of the parentheses. And so when you take this minus through, that is now negative, or comes down as minus, and so does the 30x. Okay, now 200x, 30x, they're like terms. So I'm going to write that at the front. That's 170x because it's 200 minus 30. Then I've got minus x squared over 20. And then I got minus 70,000. So there's my profit equation. So we want to find, finally, now that we can, we want to find the derivative of the profit or the rate of change of the profit with respect to time. How it's increasing or decreasing, we want to know. So I want to find dp over dt, and I'm taking the derivative of the profit function with respect to time t. So p equals 170x minus x squared over 20 minus 70,000. Okay? So when I take the derivative of p, that becomes dp over dt. When I take the derivative of 170x, well, 170x is linear. When I take the outer derivative or take the derivative of linear, it becomes a constant. And then I have to say times the derivative of the inside function because the function is a function of time t, so that becomes dx over dt. Okay? This is 1 over 20. I'll keep that. And then I'll say times 2x because the derivative of x squared is 2x. And then again, x is a function of t, so I say times dx over dt. And then this is a constant, so that just becomes 0. Okay? So dp over dt equals 170 dx over dt minus 1/10 x dx over dt. So I have dx over dt, and I have x. So I've got to plug these values in. So we know x is 4,000. It was given to us in the problem. And we know dx over dt is 600. So we're going to plug in these numbers. 170 times 600 minus 1/10 times 4,000 times 600. Putting that all in. Let's see what we get. 170 times 600 minus 1/10 times 4,000 times 600. That gives us a negative 138, 138,000. So it is decreasing. So profits are decreasing. And that makes sense because the revenue is decreasing. Costs going up, revenue is going down, lower profits. Okay? So we put that on the answer in the document or on the computer. You put decreasing here because it was negative. And then the rate value is 138,000. And again, we do not put the negative here. The negative is taken care of because we put that we're decreasing there. So this one might have even been the easiest one. Had several parts, but they gave you the functions. You just had to apply, the techniques. So I hope this clears up any questions you were having or any trouble you were having with implicit differentiation and related rates. And I will see you all again soon.